Hello everybody, my name is Marisa Khair and I work at the Soraya offices as part of the commissioning team, so we work on the MeerKAT telescope. I'm also a pulsar researcher, so for this particular session I'll be teaching you more about pulsars and we'll look at the data analysis using data from the MeerKAT telescope. So welcome again to the winter school for the students attending. This should be your second lecture on beamforming. And here we'll get to grips with pulsar astronomy and data analysis, in particular what you'll also need for the tutorial. So while this forms part of sort of a mini series, I'll also try and present this as a standalone lecture so that you will be introduced to the details of pulsars, regardless of whether you've already learned about beamforming. So let's get started. So in this lecture, we're basically going to cover sort of 4 points. We'll start by introducing what pulsars are, then we'll move on to the known pulsar population, spend some time looking at their observational properties, in particular what you will need to do data analysis using MeerKAT data, and we'll end with a topic on how we use pulsar timing to investigate space-time. So on to the introduction to pulsars. The discovery of pulsars is one of the very wonderful serendipitous stories of astronomy. So all the way back in the 1960s, Jocelyn Bell Burnell, she was then a PhD student working at Cambridge University, she was helping out building this radio telescope that you can see in the pictures. And so the aim of this experiment was not to find pulsars, but rather just to look for scintillation from compact extragalactic objects, so quasars and things like this. That wasn't very well understood at the time, and so they put in quite a bit of effort to build this massive telescope and investigate the scintillation. So everything wasn't as sorted then that you could just have digital data streaming in. Actually, data was coming in on a pen chart recorder. So you've got all this chart paper and you wait for this pen to move up and down. And after the telescope was well calibrated and finally working, her job was to try and find interference and make sure that we really understand what's astrophysical signals and what's just coming from terrestrial Earth-like sources. And in 1967, after having seen it a couple of times, she noted these pulses that she started labeling with a question mark and later referred to them as scruffy pulses. So you can see them here in the chart recording that they still keep in the University of Cambridge Museum. She's marked it as CP1919, and just to the right of it, there's another bit of scruff that's marked as interference. Now, the difference here that she noticed is that the interference actually goes up and down. So, whereas the signal that she was unsure what it exactly is just a positive signal, but it looked as if it contained maybe something within it. And she was smart enough to think of a simple solution to learn more about the signal. So you can run the chart recorder faster. And if you do that, then you basically stretch out the signal, right? So the paper goes faster and the pen still has to move up and down, and you manage to learn more about the signal. So that's exactly what she did. Here in the lower panel, you can see the stretched out pen chart. And you don't have to squint to see that there are little pulses coming in quite evenly spaced in this chart. She measured them up to be spaced at about 1.33 seconds apart. And this is quite unusual. Typically, if you see something this periodic, you'd assume that it's terrestrial, or that it's some sort of man-made signal. In fact, they would at some point consider that maybe this was aliens, little green men, trying to say hi to us. Hi. However, what she noticed that gave away that this could not be terrestrial or maybe even aliens is that it kept sidereal time. And so the source of where the pulses was coming from was moving along with the stars. And so it was changing by the same amount that a distant star would. So that ruled out that it could be coming from a near field location such as Earth. And later on, they would discover many more, which made them realize that it couldn't be alien life either. Right, so knowing that it was unlikely coming from little green men, astronomers started to investigate whether such a periodic signal with a period of 1.33 seconds could be coming from a spinning star. Because you can imagine a star spinning and emitting this pulse every time it comes around. So for us to investigate this option, let's do a couple of easy calculations. So here I'm going to draw my star. It's a spherical star, and there's two forces acting on this spinning star. The one is the centrifugal acceleration. I'm going to draw it in purple to match my equations. So that's the force that's really trying to tear material off the surface of the star as it's spinning rapidly around. If it's spinning too fast, this force will lead the particles on the surface to be torn away from it. So this force is counteracted by the gravitational acceleration. So we all know about the gravitational acceleration. That only has to do with the mass of the star itself and the gravity associated with that. So in order for the star not to tear apart, it needs to be true that the centrifugal acceleration is less than the gravitational acceleration. And we compute the centrifugal acceleration at the equator of the star because that's where it will be the largest. All right, so let's just recap what type of parameters you need for these. So the centrifugal acceleration is made out of the angular velocity squared times the radius of the star. So my star here has a radius r. And you all will recall angular velocity, which is simply given by 2 pi over the pulse period of this spinning object. And we have this pulse period. That was the one that was measured to be 1.33 seconds. Okay, so that's the centrifugal acceleration. In terms of gravitational acceleration, it's written down here. That's simply a function of the mass. So my star has some mass m, the gravitational constant g, and the radius of the star that we've already defined. So an interesting question is, given the rate at which the star is spinning, what would be the minimum density that the star could have? Right, so the stellar density rho is just given by its mass over its volume. And we recall that the volume for a sphere is, so we've got mass over 4 over 3 pi r cubed. All right, so that's the volume of the sphere, and so we've got some sort of density. And so what I'm going to do now, I'm not going to show it in full, is that you can easily see how, for example, if I rewrite this to be angular velocity squared less than gm over, I take the r to the right side over r to the cube, how I can now rewrite this equation by plugging the expression for the stellar density into here. Okay, and so let's just clear that up a bit so you can see. I'll leave that as a very simple exercise. I just want to show this equation in full. And so what they computed was that the minimum density that this rotating object could have is simply set by this pulse period p squared that they've measured and the gravitational constant. The minimum density was found to be about 8 times 10 to the 10 kilograms per cubic meters. Now that's very high, but it's still within the limit of a white dwarf. And so they were thinking, well, this spinning object with a pulse period of 1.33 seconds could maybe just be a white dwarf that in some manner is emitting radio pulsations. However, not long after the discovery of this first rotating object, many more were discovered in the 60s, including the Crab pulsar. So I'm sure many of you have learned of the Crab pulsar. It lives in the Crab Nebula, and that's the supernova remnant that was already known from long ago and discovered by the ancient astronomers back in 1054. The big difference between this Crab pulsar and the original discovered pulsar was the spin period. So just have a look at this. The spin period for the Crab is 33 milliseconds, whereas when we were just doing the calculation before, that pulsar only had about a 1.3 second pulse period. And so immediately when you do the same calculation and try and think about what the minimum density of this object is, it's going to be much larger. And so this object was found to be at least 1.3 times 10 to the 13 kilograms per cubic meters. And so this can just no longer be a white dwarf, but it did actually make astronomers page back to some theory that was written down in the 30s. This was proposed by Bade and Zwicky, an object that they already then called a neutron star that would be formed within a supernova explosion. So today, of course, we know that that's exactly how pulsars are born. Massive stars, if they're massive enough, 10 to 40 times the mass of our own sun, they will end their lives after they've exhausted their fuel through a gravitational collapse. And it's in this process of creating a supernova explosion that a dense core remains. Now, this dense core is exactly the neutron star that we are curious about. It's only 10 kilometers across and typically about 1.4 times the mass of our sun, although we're also starting to observe ones with larger masses. It's the extremeness of these dead stars that are quite captivating. So once they're formed, they spin around their own axis incredibly fast, some up to 700 times a second. That's like Mount Kilimanjaro just whizzing around in your kitchen blender. And as we saw in the previous calculations, they're also incredibly dense, up to 10 times that of nuclear densities, meaning 10 times more than what the densities of atoms here on Earth are. To boot, they also have very incredible magnetic fields, over 1 trillion times that of Earth. And even to date, the interior of them is not very well known. We know most of it exists out of neutrons, but what happens in the very core remains unknown, and there are various models suggesting things like hyperon or boson condensates or even free quarks at their center. These studies remain an area of ongoing research. So pulsars are just neutron stars that we see emitting radio beams. They're often called the clocks of the night sky or even the lighthouses of the sky. And as you can see in this animation, it's because this beam of light sweeps through your line of sight, and every time it reaches your eyes or the telescope, you observe a radio pulse. So these dead cores are not so dead. So what's happening, I'll overlay a schematic to show it to you, is that the pulsar, the neutron star, has a magnetic field, and this magnetic field has a north and a south pole. And as you can see, the radio beams are being emitted from the poles of the star. So really, the magnetic field lines at some point are no longer closed, and it's along these open field magnetic lines that you see the radio beamed emission. And every time this emission sweeps across your line of sight, we see the pulse as below. Here's a nice example of a bright pulsar called Vela. It's a southerly pulsar, so this detection was made by the Parkes telescope in Australia. And you can see the pulses come in one after the other. Now, because Vela is very bright and very close, it's only 300 parsecs away, we can even see the single pulses. But you'll shortly learn that that's not true for all pulsars. Here in particular, I show that what we really need to do to be able to make sure that we actually detect a high signal-to-noise ratio pulse is that we have to add multiple single pulses together to get this table shape. So on the right down here below, that was the Discovery pulsar we talked about earlier on, CP1919. And in this animation, what's happening at the top, we are seeing what every single pulse looks like. Whereas at the bottom, we're adding all these single pulses together. And you can see while every single pulse could be quite different from one another, the average pulse shape stays quite stable. So the advantage is that this average pulse shape has got a higher signal to noise, so it's easier to detect. There are many pulses for which we can't even see the single pulses. And the second advantage is that it's very stable, and that will become important later when we talk about pulsar timing. So, a quick interlude, we won't deal too much with this, but I'd like to mention that pulsars are very polarized sources. So I think you'll recall from your introductory lessons on radio interferometry that it's really what we're measuring when we build a radio telescope is the electric field from far field sources falling in on our telescopes. And in essence, the polarization state of these waves falling in on your telescope can be defined by the difference in the phase and the amplitude of these complex voltages that are induced by the electron field as what I've labeled here EX and EY. So in pulsar terms, often we like to talk about what's called the Stokes parameters. And so Stokes I here, the Stokes parameters are I, Q, U, and V. Stokes I is simply the full intensity of the pulse. So that's a positive quantity. Here you can see it's the square root of the other Stokes parameters. This is the square root of the sum of the other Stokes parameters. And just briefly, Q and U are often combined to give us a sense of what's the linear polarization fraction of pulsar light, whereas V gives us a handle on circular polarization. So if V is 0, then the pulsar light is fully linearly polarized. I won't go into much more detail here. You'll be able to see, if you've got a keen eye, that U is really the real part of the complex electric field, and V is associated with the complex part. And this phase phi that I've got in the cosine and the sine down here, that's simply the relative phase between these electric field vectors that I've labeled EX and EY that are inducing voltages in your receiver. Right, so here I'm showing you a pulse shape to illustrate this idea that oftentimes pulsars are seen to be highly linearly polarized. So the white shape here is just the full intensity. It's Stokes I for this pulsar. And in magenta, you can see the linear component. And you can see that that's quite a significant fraction of the full intensity. So this particular pulse is quite highly linearly polarized. And it also has some circular polarization, which is shown here in the cyan down below. So what I also want us to pay attention to is this polarization position angle that I've plotted and circled here at the top of the graph. So the polarization position angle is just the angle of the telescope receiver with respect to the plane of polarization. So recall that the incoming wavefront, you can describe the incoming wavefront in terms of its polarization plane, and that needs to be measured by the receiver, and there will be some offset, some angular offset that we call the position angle here. And as you can see in the description of the position angle in terms of these Stokes vectors, it's relating U and Q from the Stokes parameters. And really, the position angle only runs between -90 and 90 degrees. So in the top left, I've just taken the top bit of that figure and brought it down because it's really the signal wrapping. And so you can see in white this S-shaped curve. And it's the S-shaped curve that I quickly wanted us to get to, because this will tie in again with some physical understanding that we have of pulsar beam models. So when you look at, recall we've got this neutron star, it's got a strong magnetic field, radio beams are being emitted along the open magnetic field lines, and so we've got this radio beam of coherent light. If you think of these magnetic field lines as creating the plane of polarization of this beamed radio emission, then you can look down the front of the beam, and basically you'll have these plane of polarizations as I show here in magenta. And as the pulsar is sweeping our line of sight, we need to observe the sweeping beam, right? And so it's our line of sight trajectory that I've got in blue here that's cutting the beam by some pattern. And you can see how the angle of this line of sight trajectory with the plane of polarization is continuously changing. It'll increase on the one hand side away from the core of the beam, and it will decrease on the other side away from the core of the beam. And it's this change in shape that gives you that S-shaped parameter. And so observing polarimetry and polarization in pulsars is often used to try and help understand the exact emission model of how pulsars emit their radiation. Okay, so that was the introduction to pulsars, a mouthful, but it's incredibly interesting objects with very extreme properties. So I hope you have learned something. What we want to do next is just a brief look at the pulsar population. So up to now, there's about 2,800 known radio pulsars, most of which are within our Milky Way. And since we're talking about MeerKAT as well, MeerKAT has already observed over 1,500 of these. And I just want to introduce you to this diagram. It's the PP dot diagram. And so what you'll see is on the x-axis, we've got pulse period. So that tells you how fast is this pulsar spinning in seconds. And then on the y-axis, we've got the period derivative. And so that's asking by how much is the pulse period changing? So what I've probably not mentioned yet is that as pulsars age, they will spin slower and slower as they lose kinetic energy. Now their lifetime is long, and this happens very slowly. So you can see these period derivative numbers are tiny, but they're measurable if you observe enough pulsations from a pulsar. So there's kind of two groupings here. There's what I've got in green, sort of a green triangle. They're the normal or the isolated pulsars, the slowies, if you will. They have a pulse period of about 1 second or a fraction of a second. And when they spin too slowly, we no longer observe emission from them. So you can see that on the far right of the diagram, there's not many pulsars known with such long spin periods. The second group are the millisecond pulsars. So they're the really fast ones, and they're the ones that we use in pulsar timing experiments. They make up approximately 10% of the pulsar population, and they are mostly in binaries, and it's due to the fact that they are in binary systems that they are spinning so fast. So what really happens is you've got the pulsar, it's orbiting with some companion, and it's accreting material from this companion it's orbiting with. And it's through that process of accretion that the pulsar is spun up to higher and higher rotational periods. So if you look at the PV dot diagram again, you'll see, so they are in the lower left corner, which means they've got a very small period. They're spinning super fast. And they also have a very low period derivative. So they're spinning fast and they're not really changing their spin much. And so that they are by far the most stable pulsar emitters. And it's them that we'll use for timing experiments. So let's circle that. Okay. So that was just an interlude to make sure you all know that there are these two main types of pulsar populations. And now we'll get back to exactly what the data looks like that you gather in your telescope and how you go about analyzing it. All right, so the first thing to mention is that pulsars are broadband. So what that means is that we observe emission across a wide range of radio frequencies. In fact, pulsars have been observed at as low as 30 megahertz and all the way up to 230 gigahertz. Moreover, they are steep spectrum sources. So what that means is that they are brighter at low frequencies and dimmer at higher frequencies. And here I've put the sort of proportionality equation. So if S nu there is your flux, then it scales as frequency to the minus alpha, where alpha quite typically lies between 1.4 or 1.8. So let's look at the examples on this slide. We've got the Vela pulsar down here at the lower left corner. The pulsar data has already been folded. So recall that previously we said you can't necessarily see a single pulse from every pulsar. Well, Vela's bright, you can. But even if you do, you often would want to create the highest signal to noise ratio pulse shape you can. And you do this by adding pulse periods on top of one another. So that's why the X label there is pulse phase from 0 to 1. So it's really one rotation of the pulsar. And you can see on the y-axis, that's the MeerKAT L band. So the frequencies are going from around 860 megahertz up to about 1.7 gigahertz. And you see the pulse light across the full spectrum there. I've actually gone as far as to chop them up into 8 frequency channels. So that's what you see in that middle plot. And again, you can see the brightest pulse is the one in blue at the bottom. That's much taller than, say, the very top little gray one at 1.7 gigahertz. And just for a more complex pulse profile, I also have Pulsar J0955 at the top right there. It's a very broad pulse shape. And again, in that waterfall plot, you can immediately see that the emission is brighter at the lower frequencies. It's this property of pulsars being steep spectrum sources that also makes them good targets for upcoming UHF receivers. So while MeerKAT is now doing most of its pulsar astronomy at L-band, the U-band receivers are already being used and tested as well, and they're at lower frequencies. So you can imagine that the pulsar data, many of them are brighter than what they are at L-band. Right, so of course, even within pulsar data, it's not all just astrophysical, it's contaminated by radio frequency interference, as I'm sure you've learned a lot about in this winter school already. So the standard rules apply. Most of the RFI that we see comes from terrestrial telecommunication devices. And so they generally emit in quite narrow frequency bands, and they're often also quite well known to us. So here again, I've got a plot of a pulsar observation done at the MeerKAT L band. And if you just average across this data set, you can see the spectrum, the RFI spectrum. And really what we're seeing is mostly GPS and then also some GSM mobile, which I've marked with these white dotted lines as well. But underneath all of this, there's a pulsar, and the data has already been folded. That's why we've got pulse phase from 0 to 1 here at the bottom again. So if you could just get rid of these contaminated channels, you'd be able to unveil the pulsar signal. So that's exactly what you do, and out pops the pulsar we just had in the previous slide. Of course, it's often a little bit more complicated than just removing narrowband RFI. You sometimes also have to deal with sporadic temporal RFI, and so you might have to go through timestamps in your data and remove the relevant contaminated time samples. But of course, there's a lot of software suites that already help you analyze the statistics of your data and can help you get rid of these outlying interferences. So now we come to an aspect that is quite unique to pulsar astronomy data analysis, and that's dealing with the effect of the interstellar medium. You might recall from our previous lecture on how to build a beamformer that we were already discussing this impulse response function of the ISM, but here we'll recap it and we'll look more closely at how it impacts pulsar signals. So the electron densities within the ISM makes the ISM act as a frequency-dependent dispersive plasma. So you can think of it as in the same way that a prism breaks up optical light into its various frequency components. In that same way, the cold plasma of the ISM will slightly delay radio signals. Now, it's a very slight delay. At 1 gigahertz, you can basically have a signal travel 1,000 light years and only be delayed by still less than a second. But now you've learned that pulsars are incredibly fast rotating objects. And so really seconds matter. And so the signal of a pulsar, if it's being delayed by between a few milliseconds and a second, will really change the observed pulsar signal. Moreover, you've also learned that they're broadband. And so if the ISM has a different impact depending on what frequency you're observing, then it'll be true that the delay that you have, say, at the top part of your MeerKAT band will be quite different from what you have at the lower part of the MeerKAT band. And that's exactly what we see. So in this equation here, in green, we compute the expected delay between two frequency channels. So call some frequency channel frequency high and a different one, a lower frequency low. Then you can use this equation to describe by how much the two signals will be delayed between when you receive the one and when you receive the next one. The remaining quantity here is the dispersion measure, dm. So that's kind of the proportionality constant. And the dm tells you basically how many electrons the pulsar signal had to pass before it reached you. So in mathematical terms, that's the integral of the electron column density between the observer and the pulsar. And you can already start to think that, well, if you make some assumption on what is a typical or an average electron density within the galaxy, then you could use this dispersion measure quantity to infer a rough distance to a pulsar. Okay, since this is such an important aspect, I would just like to do a quick whiteboard session to make sure we all understand exactly what the interstellar medium is doing. So here I've put the equation at the top so we don't forget. And I'm just going to draw my pulsar over here. So there's the neutron star. It's emitting beamed emission along its magnetic axis. And down here, we've built our telescope that's ready to observe. And now let's use some colors. We'll have, we'll make that the lower frequency component, and we'll make that the higher frequency component. And we'll say, imagine this is the lower frequency component is a bit of a fatter pulse, and here is the high frequency emission from the pulsar. Of course, there's all the emission in between as well. I'm just picking two reference frequencies for this example. And so now the pulsar signal, these little Gaussian pulses, have to travel, probably in a straight line, from the pulsar to the telescope. And along the way, they encounter all these free electrons in the form of electron density that I'll call Ne. And it's the purple one that's going to arrive first. So if this is time, and this here is frequency, I'll just call it frec, then the high frequency one, which was purple, will arrive first. Here it is. And a little bit later, we'll have the low frequency component come in. And if we had plotted all the different pulses in between, then they would fall along this trend that goes as frequency to the -2, as you can see from that equation at the top. And the characteristic that describes this particular delay is the dispersion measure. So for every pulsar, there's a unique dispersion measure, and we need to figure that out so that we can stitch the pulses back together again. Right, here's an example where it's already been done. So again, we're looking at the Vela pulsar, which is this bright southerly pulsar with 89 millisecond pulse period. And you can clearly see the impact of the interstellar medium here. So the high frequency component is coming in first, and then here only later we find a lower frequency component. And again, as you can see from the label of the x-axis, the pulse signal has already been folded on top of one another. And because the delay of when you would have received this top signal at 1.7 gigahertz with respect to when you would receive the lowest frequency within the MeerKAT band, because that delay is larger than the pulse period, you've got the signal basically wrapping around from the folding process. But that still doesn't prevent you from correcting this. And so once you've actually figured out what the dispersion measure for this pulsar is, and you've corrected those delays, then you get back the bright pulse that you've seen before. So just a quick interlude, going back to polarimetry, even though we're not spending that much time on it, the ISM also imparts a change in the polarimetry of the pulsar, of the received pulsar signal. So the ISM is magnetized, and so this associated magnetic field through which the radio waves pass impart a small phase change on the wave. And this phase change is very small, such that we won't be able to measure the delay due to that phase change in time, but we can see it because it changes the polarization position angle. Recall that angle that gave us the S-shaped curve earlier. And if you look at the definition of the polarization position angle, you'll see that it deals with Stokes U and Q again. And in this plot below, you can see that exactly before we corrected for the effect of this phase rotation of the position angle, we had these ripples across the Q and U parameters. And after we correct for it, they disappear, and you get your true Stokes Q vector back. And what we call this rotation by the galactic magnetic field, this phase rotation, is Faraday rotation, and it's quantified by the amount by which the polarization position angle changes, again scales steeply with frequency. Here this is wavelength squared, and this parameter that we call rotation measure. And so similar to dispersion measure, you can see that this rotation measure is an integral between the pulsar and the observer. It integrates over, again, this free electron density that's in the ISM, but it also samples the parallel component of the galactic magnetic field. And this interlude was a way for me to just summarize that although pulsars are incredibly interesting objects, through both these dispersion measures that help us understand galactic electron densities, and through rotation measures that help us infer galactic magnetic field values, they are actually helping us study the interstellar medium. But back to pulsars. So if we're not studying the interstellar medium, then what we want to get to is the true pulsar signal. And so all these effects that the interstellar medium is imparting, we need to remove. And so the most simple way of removing dispersion is called incoherent de-dispersion. And basically what you do is, if you've got your data chopped up into all the frequency channels that your receiver has detected, then for every frequency channel, you just compute the delay associated with that frequency, and you correct for it in the way in which these arrows are showing us. So for the highest frequency, I'll shift it so that it's in line with the central frequency values, and for the lower frequency, similarly, I'll shift it until I can add them all back up together to create the pulse profile shape. However, you will see that there's a little bit of dispersion that I'm not able to correct. So this here is the residual smear within each frequency channel. And well, there's one easy way around this, and that's, well, not around it, but one way to minimize it, and that's to just have more frequency channels. So you can easily see the more frequency channels you have, the smaller these little dispersive smears or residual smears within the channel would be. But you can also fully correct it, and that's what we spoke about in the earlier lectures when we discussed beamforming. You can correct these ISM delays at the level of the raw complex voltages. And so in that case, you won't be fixing delays, but you'll actually correct directly for the phase change that the ISM response has had on your pulsar signal. And so in the Fourier domain, you can imagine that this phase change is basically a phase change imparted on the measured electric field. So in this equation here, we've got the intrinsic electric field as being emitted by the pulsar, the measured electric field by your radio telescope, and it's been changed through this ISM phase factor. And if you know that, you can simply correct for it by multiplying by its inverse. And now you'll remember that we've spoken about polarization, and so you'd have to do this for both both polarization components of the electric field separately. But once you've done that, and this is done early on, so not in your data processing, but as you build your instrumentation, it allows you basically to correct the effect of the ISM fully. And so within each little frequency channel here, you would now be able to even correct that interchannel dispersion. And the result is typically that you have a sharpened pulse shape with more features, and in particular, if the pulsar has complicated features within its profile, then you gain from this technique. In reality, just to preserve computation, often the beamformer will simply do the coherent dispersion for each frequency channel like this. So basically, it'll just, within each frequency channel, it will apply the correction to the complex voltages, but leave this final alignment for the astronomer to do in the data reduction process, because that's straightforward, and then you'll end up with this perfect signal again. We're not going to spend much time on flux calibration, but I would like to introduce the modified radiometer equation to you in any case, especially because many of these parameters would be known to you from your exposure to the earlier interferometry courseworks. So in this equation, basically, we can compute the expected sensitivity of our survey based on both the telescope parameters and the pulsar parameters. So here on this side, we've got everything the telescope's dependent upon. So we know that the larger the area of the radio dish, well, that impacts the antenna gain. And so the higher the area, the better the gain. The more number of antennas you have in your array, the more sensitive your telescope. Of course, the larger the bandwidth or the longer the observing time, that's also beneficial and increases your sensitivity. And then the only one that's counterproductive is the system temperature. You want this to be as low as possible. So these parameters set the sensitivity of your telescope. And so the pulsar parameters that come into play are the pulse period and pulse width. So basically, the width is the let's call it the on-pulse part of the pulsar. And you can see here, for a given pulse period, the wider the pulse shape, the higher the flux value, and the signal-to-noise ratio value is set by the off-pulse region, which you will take the RMS of this noise floor here relative to the on-pulse area. And in order for you to basically determine the sensitivity of your telescope, for example, you can see what the minimum flux is that you'd be able to detect for a given signal to noise ratio. So let's say you wanted to detect a pulse of signal to noise ratio 10. And just for units' sake, a quick way to deal with the units in this equation, if you measure your bandwidth in hertz, then the flux comes out in Jansky, or if you measure the bandwidth in megahertz, so the MeerKAT bandwidth is 850 megahertz, then you have flux here in millijansky. Okay, so let's summarize the pulsar data analysis steps. These are the things that you will work with in the tutorial. So when you are observing a known pulsar, the first thing to do is to fold the pulsar data on the known pulse period. And in the process of doing so, you will increase the signal to noise ratio of this pulse. Thereafter, it's important to remove all the radio frequency interference. So you look at which frequency channels are contaminated and you remove or you downweight those, or you apply software to help you figure out which channels or which timestamps to get rid of. And then lastly, you correct for whatever remaining effects of the interstellar medium there would be. So in the MeerKAT case, you would have set the you would have set the dispersion measure before the observation, and it would have been removed coherently. But then in the data reduction process, it's still up to you to just do that final alignment, so the incoherent dedispersion. And then after you've done that, you will have a nice looking pulse profile, and what remains are further calibrations like flux calibration or polarization calibration, which are not too important for what we're doing here. Okay, and before we get to the end of this lecture, the last fun bit is to talk about how we can use pulsars as interesting tools to conduct tests of gravity and to do high precision timing with. We probably couldn't have asked for better space-time tools than having atomic clocks up in the night sky. The best pulsars truly rival atomic clocks. And these clocks have already proven their worth over and over again. They've allowed us to do stringent tests of theories of gravity. The first exoplanet was even discovered in orbit around a pulsar. And they've allowed us to make indirect measurements of gravitational wave emission. So of course, exactly how well you can time a pulsar depends a bit on its own characteristics. It's the fastest ones that you can time best. And as you've learned from the pulsar population, it's the millisecond pulsars that spin fastest and are rotationally stable because of their high angular momentum. The current record holder is a millisecond pulsar in Terzan 5 in the globular cluster, and it spins at 716 times a second. So that's a rotational frequency of 716 hertz. Here's an animation where you can hear it go. That makes an awful sound. And so, of course, it's these really fast ones that we can do accurate timing experiments with. So now that we know which ones are good, we still need to understand exactly how do we do pulsar timing. The main idea of this process is that you try and account for every single pulse that's emitted by the pulsar. And so you never should become confused whether that was pulse number 300,001 or 300,002. And you should be able to track them well over months to year timescales. And how we do this is by creating a model, and you use this timing model to predict when the next pulse will arrive at the telescope. And then you carefully compare when the pulse actually did arrive at your telescope with when you thought it would arrive, and you use this to update and improve your model. So take this millisecond pulsar as an example. It's one of the brightest in the sky, 0437. There you can see its complex average profile shape. Let me just grab my cursor. And the accuracy to which we know the pulse period of this pulsar is given down here below. So here in the sort of 7th decimal place, this number will only change every 500 years, because recall the pulse period changes as the pulsar spins down over time. whereas we need to use our accurate timing model to update this last number around every 30 minutes. But we know the pulse period at any given time up to this accuracy, which is incredible. Okay, let me explain this idea of computing time residuals to you on the whiteboard. All right, so here we have our axis. We are observing a pulsar over time. And so we've observed this pulsar before, so we have a timing model that predicts when the pulse will arrive. Okay, and so then a couple of months later, we switch on the telescope and we observe when the pulse actually truly arrives. And we see that while the model is not bad, there's a slight offset. And so pulsar timing is all about understanding these offsets. So let's write this little difference here. This is what we're going to call the timing residuals. Residuals. And the timing residuals basically keep track of what is the difference between the model and the data. And if we understand the trends within our timing residuals, then we can improve our model. And so the ideal model is where basically there can be little changes between what the model predicts and what the data shows you, but sort of small statistical changes, not trends, as if the model is getting worse over time. So for us to be able to improve the model, we need to have a look at what the parameters are that go into the model in the first place to be able to make a prediction. So here I've put up an example of this bright millisecond pulsar we were looking at earlier, 0437, to just show you what are the types of parameters that go into creating a timing model. So firstly, the position of the pulsar. We need to know the position of the pulsar quite accurately. So this is the RA in DEC given there at the top. Then of course, as you would have seen from my drawing, it's quite obvious that the pulse period will have a strong effect on when you expect the next signal to arrive. But it's not just the pulse period, it's also, recall, the pulse period derivative. So that's given here as FO and F1, frequency and frequency derivative. And then we learned about the interstellar medium response. So there's this dispersion measure that you need to model. And so you need to know the dispersion measure well to make sure that if you're seeing differences between your timing model and the data, that it's not due to you not knowing these parameters well. There's also the proper motion of the pulsar. So pulsars, having been born in supernova explosions, can have quite large proper motions, maybe hundreds to 1,000 kilometers a second. And so again, all these factors will impact when the pulse will actually arrive at the telescope, not to mention other reference system corrections that you have to do. So you have to take into account the fact that the Earth is rotating around its own axis and the fact that the Earth is rotating around the Sun, and make sure that you've actually corrected for all these delays before your model will accurately predict when the pulse arrives. When you're looking at millisecond pulsars that are in binary systems, well, then all of a sudden you get access to this second load of parameters down here. So these are the parameters, Keplerian and post-Keplerian, that describe the binary orbit. So for example, if you've got a pulsar with another main sequence companion, that orbit will have an orbital period in, say, days. How eccentric the orbit itself is, meaning how circular or how elliptic it is, will have an impact. So if the pulsar is in one phase of its orbit, you receive the pulse signal later if it's moving away from you, and earlier if it's moving towards you, and the contrast will be larger depending on the eccentricity. And the rest of the Keplerian parameters I'm sure you're familiar with. I'm not going to go through all of them. And then in a tight binary, you can also, through experimentation, measure some of these other parameters, like is the size of the orbit changing? That's the orbital decay. Are we seeing any advance of the plane of the periastron? So that's like Mercury's periastron advance, or orbital precession that you can measure. The Einstein delay relates to how well it's like a gravitational redshift in the pulse signal. How well do we know, for example, the gravity of the the gravitational field associated with the other planets in our solar system. They'll have some sort of tug on the pulse signal. And similarly, that's true within its companion. And the Shapiro rate again refers to this gravitational interaction with the companion, where the Shapiro rate, the pulsar signal needs to move through the gravitational well of its companion, and that delays the pulse signal. So it's really these last set of parameters that start giving us a handle of being able to do tests of general relativity. So now, just to illustrate these examples, I want us to have a look at a couple of sets of residual plots and see if we can guess what has gone wrong in these experiments. So these are the 4 sets of residuals. So a reminder again, what I'm plotting here on the y-axis is the difference between when I thought the pulsar was going to arrive and when it did arrive, here given in milliseconds. And so I'll give away this one. This is clearly for a good timing model because there's no strong trend. There's just sort of statistical variance here. So your model is doing well. And as you can see, this is it's over 4,000 days. So it's doing well over many days. So in one of these examples, the period derivative of the pulsar is wrong. So I wonder if you could guess, if the period derivative is modeled wrong, what type of outcome we would see. So I obviously have to give you the answer, but hopefully there was enough pause for you to also think about it a bit. And in the case where you have the period derivative wrong, it basically means that the error in your model is going to get worse and worse and worse, because you are modeling the pulse period ever more wrongly over time. So that's what's happening here. You started off okay, but because you've got the period derivative wrong, the model and the data are just moving away from one another. And then there's one where you have the pulsar position wrong. And so I think we're familiar as astronomers for when there's incorrect positioning to look for annual cycles. And so you can see that's exactly what's going on in this one here. So there's about 3 peaks every 1,000 days. So that means every peak comes about every 350 days. So these are annular cycles. And so because you have the pulsar position wrong, you are inferring, you are either thinking you are receiving the signal earlier than you should or later than you should. And just lastly, sort of a combination of effects is if you both have the proper motion wrong, then it's basically as if you have the position of the pulsar wrong and it's getting worse with time because it's moving. And so that's this signal here. So these examples were to show you that there are many parameters going into making estimates on when you expect a next pulsar signal, but there's also many patterns emerging in when you get it wrong, and it's in this process that you're able to fit for the parameters and improve the model until the model is so good that you're able to infer interesting properties of the system. It's with one of these interesting systems that I'd like to end. In a truly remarkable piece of work, Russell, Hulse, and Joseph-Taylor were able to prove that the system they discovered was emitting gravitational waves. Now, this was back in the 1970s and was the first indirect measurement of gravitational waves, which up to then were only known through the theoretical prediction from Einstein's theory of relativity. The binary that Hulse and Taylor discovered was also the first discovery of a pulsar in a binary. And so they were quite lucky in that it contained a pulsar with a 59 millisecond pulse period, so quite a fast pulsar and a good timer, along with other non-emitting neutron stars, so 2 gravitationally heavy objects in orbit. The orbit itself had a period of about 8 hours. And they measured, studying the timing residuals of this millisecond pulsar, that they could predict an orbital precession of 4.2 degrees per year. So most of you will probably be familiar with Mercury's orbital precession. So for that system, we measure a change of about 43 arc seconds per century, whereas the orbital precession that we're seeing in this type binary is about 30,000 times greater than that of Mercury. So basically, we are measuring the same change as what we'll see in Mercury over a century in just a day in this tight binary system. The binary will also with time shrink due to the energy being radiated away through gravitational wave emission. And it's this prediction that was the most interesting piece coming out of this work. Shown here down below is a prediction by general relativity as a straight line on how the orbit should shrink with time. So you can see from 1975 to 2005, using our best understanding of general relativity, the straight line is how we think the orbit should change its size. And then on top of this, you see these dots. Now that is the data coming from, the predictions coming from the data that Hulse-Taylor had observing this millisecond pulsar. And you can see that these are in incredible agreement with one another. So it's not a fit to the data. It's simply showing how good the data is approximated by the general relativity prediction. And for this work, they were awarded the Nobel Prize, having shown that the energy loss calculated through general relativity prediction is in line with their measurements to within 0.3%. So these days, there are even more extreme systems than this Hulse-Taylor binary I ended with, and we use them to make even more stringent tests of general relativity. But if you would like to learn more about that, you'd have to join in for the tutorial where we will look at MeerKAT data of such an interesting system. So this brings me to the end of Pulsar astronomy and data analysis as part of this winter school. I hope you enjoyed it, and we'll pick it up in the tutorial.